Back again. So we talked about how important the derivative is and why it's important to be able to get the slope of a curve at a point. And what we're going to do is we're going to pick a curve and we're going to try to find the slope of that curve at a particular point numerically. Okay, there are going to be abstract ways to do this soon, and there are going to be some shortcuts that we can use to do this. But what we're going to do is, peek under the hood. So let's do this. What we're going to do is draw a curve, and we'll pick one of our old friends, let's say x squared. And I'm only going to draw the positive branch because we don't need the negative branch for what we're about to do. And what we're going to do is try to find the slope of this curve at 2. Now, nothing is drawn to scale here. I'm just using this as a way to motivate the derivative, to motivate a way to find the slope of the curve at a point. So let's pick the point 2, right, on the x-axis. So we have 2. And of course, the y-coordinate is going to be 4, right? Because if this is the curve y is equal to x squared, right, then to find the y-coordinate, all you do is you square the x-coordinate, and we get a 4, right? So here is the point 2, 4. Now, when we were talking about the slope of a curve at a point, I used the example of a ski slope, right? I drew a picture of a rolling hills, and you can talk about how it's steep at some places and it's not steep at other places, and then there are other places still that where the slope seems to level off. Okay, so why don't we go with that idea and look at the slope of the curve here by trying to imagine the slope of our skis as we're going down this hill. Well, actually, since the x-axis is oriented this way, we'd be going up the hill, but you get the idea. So let's take our skis and look at the slope of our skis. And we're going to use the slope of our skis to define the slope of the curve at a point. Indeed, we're going to draw a line that extends from this point. And the name of this line is going to be called the tangent line, borrowed from the ancient Greeks who drew tangents to circles, right? So we have a tangent line which hits this curve in one place, and that line represents the slope of our skis, and we're going to use that line to be able to define the slope, of the curve at the point. Now, again, there's a problem, right? Because if I want to use this line, which is a simple thing, to understand something more complicated, like a curve, right, I would need 2 points on this line to be able to compute the slopes. I don't have 2 points on this line. I wish I did, because if I had 2 points on this line, then all I would have to do is compute the rise of the run. So this was a great idea that kind of went nowhere. Or did it? Well, what we're going to do in order to try to get the slope of this line is ask a person being a line, who's close to this line. So perhaps what I can do is interview a point generated by picking a point really close to 2. Now, what's a point really close to 2? How about 2 1/10, 2.1? That's a point which is really close to 2. Now, once again, nothing is drawn to scale here. So, give me a little latitude, and I will try to explain what we're going to do. So what we're going to do is we're going to take this point 2.1, and then we're going to compute the y-coordinate by plugging 2.1 into x squared. And we get what? We get 2.1 has a y-coordinate of 4.41, okay? And if we compute the slope of the line connecting these 2 points, we'll have a pretty good idea about the slope of this line over here. So there's good and bad, right? The good thing is we have 2 points if I connect these 2 points. I have 2 points. And then I can compute the slope. The bad thing is that this new line isn't exactly the line we're looking for, but that's okay. Let's do it anyway, right? So I'm going to call the slope of this line M1. This is this tangent line here. We can use the notation M tan. That's a notation used in a lot of calculus books for the slope of this line here. Whereas the slope of this line I'll call M1. All right. So let's compute M1. This is not the line M1. The slope is M1. So let's compute it. So we have M1 is equal to, well, like I said, the good news here is we have 2 points, and we can use these 2 points to find the slope of the line that's nearby our tangent line. So doing so, we have 4.41, right, the change of y, so minus 4, over the change of x, which is 2.1 minus 2, which gives us, I'm going off screen, it's okay, 0.41 over 0.1, which is equal to 4.1. Okay, I'm back. So like I said, there's good news here, right? The slope of this line, which is close to the tangent line, is 4.1. Well, okay, that's good. And we could call it a day, but we're not, okay? And what we'd like to do is see if we can do better. In other words, can I find a line that's even closer to the tangent line? Well, of course, we can do so by picking an x-coordinate that's even closer to 2. Remember, 2 is the point at which we would like to find the slope of the tangent line, okay? So I'll darken that in a little bit. We want to find the slope of this line. We found a slope of a line who's a good friend of this line, but not good enough. We can find a friend who's even closer, as I said, by picking the point maybe 2.01. So let's do that. 2.01 is 10 times closer to 2, because this is 2 and a tenth, this is 2 and a hundredth, right? So let me draw what would happen if I were to take 2.01 up to the curve, right, by computing the y-coordinate, and then drawing a line M2. Well, M2 is not the line. M2 is the slope of that line. So I want to find the slope of M2. Notice that this other line, these are called secant lines, by the way, right? So the first secant line, M1, is close to the tangent line, but M2 is even closer. Therefore, when we compute the slope of the second line, we'll get a slope that's even better. That's an even better approximation of the slope of the tangent line. Get the idea? You see, what we're going to do is find the sequence of lines that gets closer and closer and closer to the tangent line, which will induce a sequence of slopes that will get closer and closer and closer to the value of the slope of the tangent line. Let's do it. So we have the coordinates. This diagram is getting a little bit cluttered, but the coordinates of this point are going to be 2.01, 4.01, 0401. Okay? There's a little pattern here. You see the zeros are getting interspersed in between the 4s and the 1s. This is not my first rodeo. I've computed these values before. But anyway, we can go with it, right? So the slope of the second line, which we'll denote by M2, all right? There we go. This is our x-axis. And M2 is going to be equal to 4.0401 minus 4 over 2.01 minus 2, which is going to give us 0.0401 divided by 0.01, which is after multiplication of top and bottom by 100, we get 4.01. Okay? Wow. So look at that. The slope of the first line is 4.1. The slope of the second point is 4.01, right? And the second line is closer to the line that we're looking for. 4.1, 4.01. Want to bet what happens if we pick an x-coordinate of 2.001? Well, you are all very smart, so you're probably going to figure it out, right? Be 4.1, 4.01. What do you think? We're going to get 4.001? Yes. But I'm not going to clutter up the diagram. We'll do this on the side, all right? So if we picked a point 2.0, a point for which the x-coordinate is 2.001, what would we get? We would get y-coordinates, which would be, well, yeah, all right. I won't clutter up the diagram with another line, or maybe I will. What the heck? Another line is going to come out like this, all right? And this will be the third line for which the slope is m3. Now, the coordinates of that point are going to be 2.001 and then 4.00401. Like it? And, oh, this is incorrectly denoted. It should be M3, right? Good. So then the slope of this new line, which you can see is closer still to the tangent line, to the line whose slope we want, right? M1, M2, M3. We want the slope of the tangent line. Let's get the slope of the third line. So the slope of the third line, M3, is going to be equal to 4.004001 minus 4 over 2.001 minus 2, which is equal to 0.004001 over 0.001. And after multiplying top and bottom by 1,000, you guessed it, we get 4.001. And that's M3. Well, this is very suggestive, right? It's suggestive of the idea that the slope of the tangent line is going to be 4, right? We pick the slope nearby, got 4.1. Slope of the line even closer, 4.01. Slope of the line that's closer still, we get 4.001. Yes, the slope of the tangent line is going to be equal to 4, except we need a whole lot of machinery to be able to substantiate that. But hopefully you get the idea from this drawing that, you know, this is a real thing, right? We really want to get the slope of this tangent line, and all we need to do is pick lines which are closer and closer and closer to the tangent line and use the slopes of those lines, right, to get the slope of the line that we want. Good.